There is something on your refrigerator right now that your physics teacher almost certainly never fully explained, not because they were hiding anything, but because the complete explanation reaches so far down into the structure of reality that it touches quantum mechanics, special relativity, and questions that professional physicists still argue about. A fridge magnet holds a piece of paper against a vertical surface all day without any power source, without fuel, without wearing out. And that fact has become so ordinary to you that it stopped being strange. But notice what is actually happening. Gravity, the force responsible for the orbit of planets, the collapse of stars, the large-scale structure of the entire observable universe, is being casually defeated by a thin piece of ferrite ceramic the size of your thumb every single day in your kitchen. That asymmetry deserves a closer look. Here is the first thing to understand, and the first misconception to quietly set aside. When that magnet holds against the fridge, it is not fighting gravity on equal terms. The magnetic force in that small contact area locally overwhelms gravity for light objects. But try sticking something heavy to your fridge with a weak magnet, and it falls immediately. The reason a fridge magnet works is not that magnetism is stronger than gravity in some cosmic sense. It is that magnetic force concentrates in a tiny region, operating over short distances between closely packed atoms, while gravity is a long-range force spread across the entire mass of the Earth below your feet. They are not really competing. They are playing different games, and the magnet wins the local game it happens to be playing. The textbook answer, electrons creating magnetic fields as they spin, is correct, but it hides something extraordinary in plain sight. When physicists say spin, they do not mean what the word implies. An electron is, as far as every experiment ever conducted can determine, a point particle. It has no physical size. It is not rotating the way a basketball. There is no surface to spin, no axis to turn around. Quantum spin is an intrinsic property of the electron itself, built into what the electron fundamentally is, and it has no classical analogy that fully captures it. The electron behaves as if it were a tiny magnet, as if it had angular momentum from rotation, even though it is not rotating in any physical sense. This is not a gap in our understanding. It is a feature of quantum mechanics. Some properties simply exist at the fundamental level, without a mechanical explanation underneath them. This is what Richard Feynman was pointing at when he said, in effect, that nobody really understands magnets, not at the level of why does spin exist, why does charge create fields at all. At that depth, physics describes with extraordinary precision what happens. The question of why it happens that way touches the edge of what the framework can answer. Every electron in the universe carries this intrinsic magnetic moment, including the electrons in your hand, your coffee cup, the air you are breathing, every single one. And this raises an obvious question. If every electron is a tiny magnet, why isn't everything magnetic? Pause and predict what happens next. In most materials, electrons pair up in atomic orbitals, one with spin pointing in one direction, one with spin pointing in the opposite direction. The magnetic effects cancel almost perfectly. Billions of tiny magnets paired into near-perfect silence. The magnetism is present. It is simply organized into mutual cancellation. The material is magnetically neutral, not because it lacks magnetic electrons, but because those electrons are arranged to oppose each other completely. In iron, cobalt, and nickel, something different happens. And the reason it happens is one of the most underappreciated facts in all of materials physics. It is not simply that electrons decide to align. There is a quantum mechanical reason, and it comes from an interaction called the exchange interaction. Here is how it works, without the mathematics. Electrons obey the Pauli exclusion principle. Two electrons with the same spin cannot occupy the same quantum state in the same region of space. This means that when two electrons near each other have parallel spins, they are forced by quantum rules to stay somewhat spatially separated. Being farther apart, they experience less electrostatic repulsion, which lowers the total energy of the system. The result is an exchange energy that, in iron and a few other materials, actually favors the aligned configuration. The electrons are not aligning because they are attracted to each other magnetically. They are aligning because quantum statistics combined with electrostatic repulsion makes parallel spin the energetically cheaper option. This is a simplified explanation to make the core idea intuitive, but the underlying mechanism is real and purely quantum mechanical. Regions where this alignment occurs are called magnetic domains, volumes of material where millions or billions of electron spins point in the same direction. In an unmagnetized piece of iron, those domains point in different directions, and the bulk magnetic effect cancels out across the object. When you bring a strong external field near the iron, the domains that happen to be aligned with the field grow at the expense of the others, and the material becomes magnetized. But here is the point, the dramatic opening almost obscured. The aligned state of a permanent magnet is not a perfectly stable, eternal condition. It is metastable, a local minimum of energy, stable enough to persist under normal conditions but vulnerable to disruption. Heat the magnet past a specific threshold, called the Curie temperature, around 770 degrees Celsius for iron, and thermal energy will randomly jostle those domain alignments apart. The magnet loses its magnetism entirely. You can also demagnetize a magnet with a strong opposing magnetic field, or with repeated mechanical shocks. Drop a strong magnet hard enough, and you will measurably weaken it. The fridge magnet does not run on power in any electrical sense, but it is not indestructible either. It is maintained by the stability of quantum-level alignments, and those alignments have limits. Now, the compass. This is where the story scales from atomic to planetary, and where several more common misconceptions cluster. You were told a compass points north because of Earth's magnetic field generated by the molten iron outer core. That is broadly correct. Liquid conducting iron churns in convection currents driven by the heat of the inner core, and those moving charged particles generate electrical currents, and those currents generate a magnetic field that extends far into space around the planet. The entire mechanism is called the Geodynamo, and it is one of the more extraordinary self-sustaining processes in nature. But here is what most people were never told. Magnetic north and geographic north are not the same. The magnetic pole is currently located somewhere over the Canadian Arctic, and it moves. It has been drifting at an accelerating rate for decades, moving roughly 50 kilometers per year in recent measurements. Your compass has never pointed to the actual top of the globe. It points to where the magnetic field lines currently happen to dive straight into the Earth's surface. That location is always shifting. Earth's field is also flipped completely. North becoming south, south becoming north. Hundreds of times in geological history, the evidence is preserved in the orientation of magnetic minerals in ancient volcanic rock, frozen in place at the moment the rock cooled past its own Curie temperature. The last full reversal was approximately 780,000 years ago. These reversals take thousands of years to complete and are not sudden catastrophic switches. The answer requires being careful about language. The compass needle always aligns with the local magnetic field. What we call the north-seeking end of a compass needle actually points toward magnetic south, because opposite poles attract, and Earth's geographic north currently houses what is, magnetically speaking, a south pole. A full reversal would move that magnetic south pole toward geographic south. The compass needle's north-seeking end would follow it there. In practice, you would either rename compass directions or reprint every navigation chart ever made. The physics stays the same. Only the labeling changes. Now, what about the weakening of Earth's field? This has been documented, and it is real. The global dipole has weakened measurably since systematic measurements began in the mid-19th century. There is also a region called the South Atlantic anomaly, where the field is significantly weaker than the global average, and that region has been expanding. It now spans an area comparable to roughly half of Europe in some measurements, and the weak field there is causing practical issues for satellites passing through it. Increased cosmic ray exposure, electronics disruption. But it is important to be precise here. The weakening and the growing anomaly are not, by current scientific consensus, solid evidence of an imminent reversal. Reversals take thousands of years. The current weakening could be a temporary fluctuation. The field has been weaker before and recovered. There is ongoing scientific debate about whether we are entering a precursor phase, or simply experiencing normal variation. Any claim of certainty in either direction goes beyond what the data currently supports. Now, here is the deepest conceptual shift of the entire subject, and one that requires a small but important correction to a popular way of explaining it. You may have encountered the idea that magnetism is simply electricity seen from a different reference frame. That if you apply Einstein's special relativity to a wire carrying current, the magnetic force a moving charge experiences is actually just the electric force, transformed by the relativistic compression of space. It is a genuinely beautiful demonstration, and it illustrates real physics. The key insight, that electric and magnetic phenomena are aspects of a single underlying electromagnetic field, is one of the great intellectual achievements of the 19th and 20th centuries together. But the stronger claim, that magnetism is nothing more than a relativistic correction to electricity, is an oversimplification that physicists are careful about. Both electric and magnetic fields are fundamental components of the electromagnetic field tensor, a single mathematical object. In different reference frames, different observers measure different proportions of electric and magnetic field, but neither is more fundamental than the other. And in permanent magnets, the dominant source of magnetism is quantum mechanical spin, which involves relativistic corrections of a much more intrinsic kind, not simply the motion of charges through a wire. The unification is real and profound, but it is a unification of equals, not a reduction of one to the other, and the applications of this unified force are almost incomprehensible in scope. The electric motor, which powers everything from subway trains to the cooling fan in a laptop, operates entirely on the interaction between magnetic fields and current-carrying conductors. Generators do the reverse. Mechanical rotation becomes electrical current through the same field interactions. MRI machines use superconducting electromagnets, producing fields tens of thousands of times stronger than Earth's field, manipulating the spin of hydrogen nuclei in your body to produce anatomical images without radiation. Hard drives store data as patterns of magnetic domain orientation on a spinning disk, ones and zeros, encoded in the same domain physics as a fridge magnet, scaled to nanometer precision. Speakers convert electrical signals into physical vibration through magnetic force acting on a voice coil. Your credit card stores information in a strip of magnetic material, and the magnet itself, the fridge magnet in particular, is almost certainly not pure iron. It is most likely ceramic ferrite, a compound of iron oxide, or possibly a flexible rubber-bonded ferrite composite. Neodymium magnets made from an alloy of neodymium, iron, and boron are far stronger, strong enough to cause serious injury at larger sizes, but they are also brittle, prone to shattering under impact, and highly susceptible to corrosion without a protective coating. The material science of permanent magnets is its own deep field, and the choice of magnet material is never arbitrary. There is one more layer worth acknowledging: Gauss's law for magnetism, one of Maxwell's 4 equations that completely describe classical electromagnetism, states mathematically that the divergence of the magnetic field is always zero. In plain language, magnetic field lines form closed loops. They never start or end, they always return. This is equivalent to saying that magnetic monopoles, isolated north or south poles with no accompanying opposite, do not exist, at least as far as every experiment ever performed has been able to determine. Some extensions of particle physics, including certain grand unified theories, predict that monopoles must have been created during the extreme conditions of the early universe. Physicists have searched for them. One candidate detection was reported in 1982, a single event, never reproduced, still debated. The theoretical prediction is strong, the experimental evidence is absent. The universe appears to insist on its paired pole rule at every scale we can measure, all the way down to the single electron. That gap between the theoretical expectation and the experimental silence is not a failure. It is a live question at the frontier of physics, one of those places where the map ends and the territory continues. And that is where this leaves you. A fridge magnet operates through quantum spin, a property so fundamental it has no classical explanation. It maintains itself through an exchange interaction rooted in the Pauli exclusion principle. It exists in a metastable state that a kitchen oven could destroy. It participates in a force unified with electricity at the level of space-time itself, a force that powers every motor and generator on Earth, stores every piece of digital information ever created, and allows a machine to see inside your body without cutting it open. The compass needle that guided human navigation across oceans for centuries points not to a fixed geographic location, but to a drifting, fluctuating, historically reversible feature of a planetary storm of molten metal. A storm governed by the same domain physics as that magnet on your fridge. None of this is magic, but all of it is deeper than the surface suggests, and the pattern, something familiar concealing layers of increasing strangeness the further down you look, is not unique to magnetism. It is a feature of reality itself. Every limit you reach in understanding is just the floor of the next room.